Hi, my name is Griffin Price, and this is Lab 3 Magnetic Field of a Bar Magnet. To introduce this lab, we're going to talk about its purpose, and the purpose of this lab is to explore the Biot-Savart law. This correlates to how distance can affect the magnetic field from a small bar magnet, and some fundamental principles that we're going to use in this lab would be the Biot-Savart law, um, the magnetic field due to dipole, and superposition. And as you can see in the top right there are some previews of my results. Now, as far as the experimental procedure, using an app, we found the X and Y location, the coordinates of the magnetometer. Right, we used a special app that it listed in the lab to do this, and we used a piece of tape and a ruler. Um, and that was that's that left hand image you see there. And the right hand image, we used equal lengths in the x and y direction, and using those links we found corresponding bx, by, and bz magnetic fields. Plugging that into a data set, we found this is for that picture from the left side or left hand image. We can find the average distance, that average r in meters. We also found average bx and lnr, lnbx, and using the two ln's, I could make this graph, right? And basically from this graph and using that equation in the beginning, I've got that n is equal to negative 2.4417, k being equal to e to the negative 13.837, which is that constant, which is 9.787 times 10 to the negative 7. And using those two, I calculated the dipole moment, um, or the magnitude of my mu, to equal 4.8936. Okay, now the off-field data. Now this was that right-hand image from the experimental procedure. Um, we put our data into these tables, and it calculated the bx component, the by component, and the bz component, the magnetic field, um, for that magnetic or magnet bar. Um, and now this is where we get into the code. So that first section of code you see towards the top there is just me plugging in some physical constants. You can see I plugged in my number I got for the mu, 4.8936. And towards the bottom you see a function that, given mu and r, your distance r, it actually finds the magnetic field, um, given whatever mu and r. Um, Now this code to the left here is just creating some vectors, some visual representation, and that's kind of the same toward the right, where these vectors are the actual magnetic fields, um, and distances that we're going to be seeing. And this right here is actually this calculates the dipole, the dipole magnetic field of the magnet mu, and our distance of 45 degrees, um, and prints it out saying B at 45 degree at distance D is equal to, whatever. And we'll see what that is here now. And as you can see, the B from our experiment, the magnetic field being 5.533 times 10 to the negative 5, 1.54 times 10 to the negative 4, and negative 2.7 times 10 to the negative 5. That's what we calculated from the experiment. And from the coding, we get something very similar. We get 5.05 times 10 to the negative 5, 1.514 times 10 to the negative 4, and 0, as you can see to the right, that visual representation. And I would say that, the magnetic field we got from the experiment and magnetic field we got from the coding, not too far off. So pretty good job. As for the what if questions, what if you hadn't orientated your experiment to compensate for magnetic north, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? The magnetic field of the Earth would definitely affect the results. The values found would be totally different, and if the experiment was conducted in this manner. And if we were to stick two identical magnets together end to end and run the experiment again, how would you defer? I feel like the directions of the magnetic fields would be the same, but the magnitude should be increased from what we previously saw.